Good afternoon. Welcome to the lecture of the elementary principles of the chemical processes. It's been a long time since last time we met, right? So let's have a quick recap what we have learned last week. Last week we learned how to do mass balance in terms of molecular species balance and atomic species balance, and also external reaction. And among these three, you understand, most important thing is do the DOF first. Without DOF, you don't want to do your calculations straightforward. No. If DOF doesn't equal to 0, then you don't need to do calculation. Okay? So that's why we introduce you the DOF for molecular species balance, DOF for atomic species balance, and DOF for external reaction. So for the molecular species balance, there are 4 terms in the DOF, right? The first term is unknown. How many unknown species, right? For example, here there are 5. And then this is plus. And then you have plus what? Independent chemical reactions. How many independent chemical reactions? For example, this question involves 2 chemical reactions. So you have to add 2 here. So 5 plus 2. And then after that, you have to minus independent molecular species balance. How many species in this reaction, in this process? So in terms of this question, there are 6 species. So they are methane, oxygen, carbon monoxide, carbon dioxide, water, and nitrogen, right? And the last term is other equations related to unknown variables. That means what? There are 3 directions you need to find. You need to find, right? Specification, physical laws, and physical constraints. There are 3 directions for you to find equations. So in terms of this example, you have a conventional method, which is specification. Okay? So remember, for the molecular species balance, there are 4 terms for you to do DOF. And then for the atomic species balance, you also have 4 terms. The first one is unknown. Again, that's the simple one. Okay, the second one is how many independent atomic species balance. So you need to remember, atomic species balance is not methane, oxygen gas, nitrogen gas. It's not. It's carbon atom, oxygen atom, and hydrogen atom. So you do input equal to output, not using methane input equal to methane output. Instead, you use carbon input equal to carbon output, hydrogen input equal to hydrogen output. Okay? So this is the one. And the third term is that molecular species balance on independent non-reactive species. For example, nitrogen in this case is not a reactant in this process. So nitrogen doesn't involve any chemical reactions. So you can have nitrogen gas input equal to nitrogen gas output. So you do molecular species balance for nitrogen. Okay? And last term will be other equations related to unknown variables. Again, 3 directions: specification, physical laws, and physical constraints. Okay? So there are 4 terms here, remember. And then for the extent of reaction, for the extent of reaction to do DOF, there are 5 terms. The first one, again, is unknowns. And you have to plus what? Independent reactions. You might say, well, Professor, why is plus? Because you need to consider about XC, right? XC, external reaction. There are 2 reactions. Right, and then you have to plus independent, you have to minus independent reactive species. How many independent reactive species here? Okay, like this one, it's not involved nitrogen. Okay, and then independent non-reactive species. Okay, and then other equations related to unknown variables. So there are 5 terms for the extent of reaction for you to do DLF. So please remember this. And then in your midterm exam, we will have a question for you to do the mass balance. And that question will involve chemical reaction. So you need to remember how to do DLF first. And then last week, the end of last week, we talked about product separation and recycle. We already learned how to do recycle, remember? Like this. Like this is a recycle stream. You already learned this. And then we learned a very important concept, which is overall conversion and a single pass conversion. So this is recycle stream. So overall conversion is you are talking about overall conversion is that you are talking about the overall input and overall output. So you have a definition of the reactant input to the process minus reactant output from the process, divided by what? Reactants input to the process. So in the case of this process, you have 75 here, minus 0 here, and divided by 75. So the conversion rate is 100%. Okay, so this is overall conversion. For the single pass conversion is that we are only think of dealing with the reactor here. So that will be the species in the reactant input to the product and reactant output from the products. Okay, so in the case of the 125 here, so this will 100 minus 25 divided by 100. So the conversion rate will be 75%. Okay, so these are the important two overall conversion and single pass conversion, and we are going to use this as we are going to use these 2 terms to do the example today. Okay, so today we start from this example 4.7-2, dehydrogenation of propane. Dehydrogenation of propane is that this one this is dehydrogenation because you lose one mole of the hydrogen, and it become propane. Okay, right. So this is the example 4.7-2. Let's take a look of this example, and I hope you already have a copy of this example. And let's read the example together. And I want you to work with me step by step, so it will be easier for you to understand how to do your questions in your exam. Okay. Right. So if you have a textbook, please go to the page 129, and then example 4.7-2, dehydrogenation of the propane. Okay. So the propane can be dehydrogenated to form propane in a catalytic reactor. So catalytic reactor is that you put catalyst into the reactor. So catalyst doesn't involve any reactions, but you will enhance to reduce the activation energy, and so you can have easy chemical reactions with catalyst. So that means C3H8 becomes C3H6 plus H2. Okay, so let's go to the second paragraph. A process to be designed for a 95% overall conversion of propane. So we need to design a process. I want to have over 95% overall conversion rate. Okay, so the reactor products are separated into 2 streams. The first stream, which contains hydrogen, propane, and propane, and the 0.555% of propane that leave the reactor. So we want to know that if we know this, let's write down what we learned from the textbook. Please take a look of the slide with me. So as we know the overall conversion rate is 95%. So that means what? This propane, if the 100 mole propane go into this reactor, that will be 5% propane come out, right? That's why conversion rate is 95%. But you know this is kind of specification. We know, let's remember this. Specification for the input here and output here. Okay? And then we understand this propane go to the reactor, and then because the conversion rate is not good, so you have a separator to return the propane back to the reactor. So this is recycle stream, right? So, but according to the description, we understand the reaction product, and this is string 1, we have products, and then we know that the product will be what? This is what we know, that the product will be propane. This is the same, right? So conversion rate, you know this, and you have propane C3H6, and you have hydrogen. Okay? And then string 2, we understand you will have this and no hydrogen. Right? No, let's take a look. That 0.555% is the specification. Let's remember this. Right. So let's back to this. Sorry, we haven't go to this far yet. Okay, so let's go to the second paragraph. The end of the line 2 is taken off as a product, so we know this is a product, right? Okay, and this is 0.555% here, propane here. So this is another specification. Okay, in the second stream, which contains the balance of the unreacted propane and the propane in an amount of equal to 5% of that in the first stream. So this is another specification related to recycle stream and the product stream on the slide. Okay? So this is the third specification. Okay, of that, the first streams is recycled to the reactor. Okay, calculate line 4, end of the line 4, calculate the composition of the products, the ratio, and the single pass conversion. So you know the overall conversion. Now the question asks you the single pass conversion. Okay, so according to the information we know, there are 3 specifications. So let's write down these 3 specifications here on the flow chart. So we know the output is this, and the recycle stream, there are only 2 products. There are only 2 species, no hydrogen, because the text tells us there is no hydrogen. Okay, and then of course when you do the recycle, you will have propane, and no hydrogen. And then when you come out here, you have propane, and hydrogen. So this is what we know about this process. And then there are 3 specifications. Okay, that's right. The basis is that there's no basis. There's no number, there's no moles or any things here. So we assume the basis is 100 mole here. Please remember this number. There's no number in the example, so you need to give a basis here. So what's 100 mole? So 100 mole here, and then you start to write down unknowns. The first one here is N1 and N2. So here is N3, N4, N5, and then N6, N7, N8, N9, and N10. You might say, well, Professor, is a little bit different because before we write down is the total amount and the fraction. But of course, that's because it depends on the question, right? You can write down in the fraction way, or you can write down in the moles for the individual species. Okay, so you have 10 unknowns here. And let's write down the specification. The specification, the first one is overall conversion, right? First is 95%, which is what? 100 divided minus 6 N6 divided by 100. So bingo, you can get N6 first. But this is not the point, because we need to do DOF. You need to sort out, you need to find out all the answers, right? Okay, so leave this as a specification. Okay, and then the second specification is that this one is about 0.555% of this one. N6 is about 0.555% of this one, of N3. So this is the specification between N3 and N6. Okay, so this is a second specification. Okay. How about the third specification? Is that this one is about N10 is about 10% of 5% of this N7. So you realize the majority of the propane is come out from this way. The majority of C3H8 propane is come from this way, because this very little amount. This is very little amount, right? But anyway, you need to find out the number. You need to find out the number. Okay, so this is all we know. So for this example, the basis is that you write down all the unknowns, and then you have three specifications. The first specification is related to this one and this one, this one and this one. The second specification is related to this one and this one. The third specification is related to this one and this one. The second one is this one and this one. The third specification is related to this one and this one. Okay, so let's do DOF first. Let's find out whether we can get the answer of these 10 unknowns. Okay, so the key is that if anything involves chemical reaction, if the system involves chemical reaction, we suggest you to do atomic species balance. For example, if you do overall unit system, and this overall unit system involves reaction, then you do atomic species balance. If you only do separator here, a separator, this system doesn't involve any chemical reaction, so you do molecular species balance. Okay, so atomic species balance for this system, atomic species for this system, molecular species for this system, molecular species for this system. You might say, Professor, where is the external reaction? Where do you want to do the external reaction? In this, as I just told you last week, external reaction is good for you when you do the computation. If you do it by hand, you better do you better do it atomic species balance or molecular species balance. Okay. So non-reactional subsistence, you do the molecular species balance. Right. So let's take it logical. Let's think of this question logically. First of all, you always think of overall, right? Overall system. Overall system. Overall system, you need to do atomic species balance. So DOF will be 4 terms. The first term will be unknown. So please tell me how many unknowns in this case. Please. Anybody want to tell me? 3, right? 3. Okay. So that will be N6, N7, and N8. So how many independent atomic species balance you can use? How many? In this system, how many chemical reaction species you can use? 2, right? What? Carbon and hydrogen. Carbon input equal to carbon output. Hydrogen input equal to hydrogen output. So carbon and hydrogen. So how many molecular species balance? There's no. This always involve chemical. This species involve chemical reaction. So there's 0. right? So how many specifications related to input and output? 1, right? 1. This overall conversion. Remember overall conversion related to N, this one and the N6? Sorry, so that's right. Okay. So you have 3 equations, you have 3 unknowns, you have 3 equations. Bingo, you can get these 3, and you can get N6, N7, and N8. And I change the color from red. I change the color from red to blue. That means you already solved this problem. You already get the answer of these 3. Okay, and you do it step by step. So once you get the answer of these 3, and then now what you need to do is you do a single unit system. Right? Single unit system. Can you do that for me? First one, you do a separator. You have 2. For this one, there are 4 unknowns you cannot solve. For this one, you cannot solve. For this one, if you think of, you have 4 unknowns for this, you have how many? 5 unknowns for reactor. You have 5 unknowns in separator. But how you have 2 specifications for this one and this one, this one and this one, right? So it's easier for you to do the separator first. So when you do a separator, again, that's molecular species balance. They are involved 4 terms, right? First one, unknowns. How many unknowns here? For the separator, how many unknowns? N3, N4, N5, N9, and N10. So there are 5 unknowns. Okay, how many chemical reactions? 1, right? 1. So you have, 0. I'm sorry. There's no involved chemical reaction here. So that's 0. Okay, and independent molecular species balance. How many independent molecular species involved? 3, right? 3. C3H8, C3H6, and H2. And please tell me, do they have specification? How many specification here? Remember that this one is 0.555% of this one, and this one is 5% of this one, right? So you have 2 specifications. So 5 unknowns, 5 equations. You get the answer. You get these 5. Okay, so you get these 5, and I change the color from red to blue. That means you do simple calculation. You can get these 5, and you can get these 5 numbers. And then after that, you do this, and after that, so now you get the answer of these 3 using the overall conversion, overall system, and you get this 5 answers using the separator, input equal to output, right? And then now you can use the mixing point here, or you can use the reactor to get these 2, because 2 species, input equal to output, easy. Right? So you can get these 2. I don't want to waste your time. Please go home and do it by yourself. So do the calculation, you get this, and then the question want to ask the conversion, the ratio of the mole recycle and the ratio to the mole fresh. So it will be what? N9 plus N10, and 9 plus N10 divided by 100. So recycle stream and input stream, right? Fresh feed. So this is the answer. And single pass conversion, you know this, right? C3H8, that's N1 minus N3 divided by N1. That's single pass conversion. Right, so please do this by yourself. So what I want to tell you is that this is the answer. these numbers, these are our answers. Then 995, 4.75, this one, these are our answers. After you do the calculation, I tell you this is the answer. And then the interesting thing is that when you do the single pass conversion, you realize 995 minus 900 divided by 995. Now we're only 10%. That means what? That means the reaction is very bad. You know, if you 995 to become 900, so you only have 95 moles of the C3H8 reacted. So single pass conversion is only 10%. However, when you think of so there are 99.5% C3H8 recycle. So this 900 become 895 and 5 moles. So this separator is very good. Right? This separator is very good. Most of them recycle, only a little bit come out. So you have a very bad reactor, but you have a very good separator. And then, as a result, you got a very good overall conversion. So what does this story tell you? In order to have a very good overall conversion, you can have a very good reactor. Or you can have a very bad reactor plus a very good separator. Right? Alternatively, it depends on how much money you can spend from the plan A and plan B. Plan A is a very good reactor. Plan B is a very poor reactor plus a very good separator. Right? This is what engineering need to think. Which one can save money and give you more perfect? Okay? So a high overall conversion can be designed the reactor to yield a high single pass conversion. So you can have a very high single pass conversion. As a result, you can have a very high overall conversion rate. Right? Or you design a reactor yield a low single pass conversion and follow it with a separator unit to recover and recycle the unconsumed reactant. Okay? So what you need to think is money. Right? Money, and speed. Money and time. Okay? And money involves what? How much money you need to build out a separator and a pipe and the fittings, pump. Okay? And is this reactor expensive? If this reactor is very cheap, you don't care. Right? You don't care about separator at all. Okay, so this is another concept of the recycle stream. So next topic we want to talk is purging. Right, so I hope you still remember this is, you have reactor, you have separator, and this is recycle stream. Right, this is fresh feed, this is product. We just learned this. So what's the where is the purging stream? Purging stream is this one. So when the product come out to the separator and is split into two. One is the recycle stream, one is purging stream. You might say, wow, Professor, why we need purging stream? So now you learn three streams which are very important. First one is called recycle stream. Second one, remember, bypass stream. Bypass. What is bypass? Before fresh feed go to any reactor or any unit, it's come out and join the final product. This is called bypass stream. And now you learn the third stream, which is purging stream. This is a purging stream. You might think, why we need it? And you know the purpose of recycle stream, I just told you. And you know the bypass stream, right? Because of, if you think of the fresh juice, want to ship from Taipei to Tainan. Wow, that's too short. want to ship from Japan to Taiwan or want to ship from America to Taiwan, especially, Trump now is very aggressive to get money for United States, right? Anyway, and you need to have a bypass stream, okay? Right, so why we need purging stream? This is a story. For example, this is a reactor, and this reactor needs oxygen to become another product, which is B. Okay, but if this reactor needs oxygen, will you introduce oxygen into this reactor, or you want to introduce air into this reactor? Which one you will choose? Of course, air, because it's cheap. Air you can suck from the atmosphere, ambient, and then you can just have a pump and put it into the reactor. And you don't want to use pure oxygen. Why? Because pure oxygen costs money. So once you have air and you pump air into this reactor, and the nitrogen doesn't have any chemical reactions in this place. And nitrogen doesn't come out as a product because product is B. So what happened to nitrogen? Where is the way out for the nitrogen? Nitrogen will, if there is no purging stream, nitrogen will be recycled and recycled all the time. And as a result, you have input and you don't have output. What happened? Please tell me, if you do this experiment or if you are running this reactor, I don't want to be with you because one day you will explode. The pressure will build up in this system and you will explode. And your life is in danger. Right? So you need to release some nitrogen out from this system. So this is the reason we need purging stream. Okay? This is the reason for purging stream. So release the undesired products and substance. In this case, it's nitrogen. And if there is a non-reactive materials in the process, the purge is necessary. Otherwise, the material will accumulate in the process until it's shut down. This unreactive reactant will leak or explode in somewhere. The pipe might be broken. Okay, so how can we do mass balance using using this purging stream? This is what we call splitting point. Remember this splitting point? Splitting point here, split from A stream to the B and B streams. And if you have splitting point, the important thing is what? The important thing is the fraction will be the same. Right? Fraction for this A stream and B stream, the fraction will be the same. This is the key, and please remember this. Okay, and this is the mixing point. So this is another unit. This is another unit. Okay, so this is one of the example I want to show you here is that remember we have A plus oxygen become B. But if you use A as a C2H4, B is the ethylene oxide, which is C2H4O, and you introduce air into this system. So as you can see, the nitrogen will, because nitrogen will be recycled, and you need to release some of the nitrogen out. The product here is liquid, and the recycled stream is all gas in the gas phase. So this separator is very good. You just separate gas and liquid. So this is what? The separator is called what? Condenser. Right? You condense C2H4O as a liquid, and you can release all the species in the gas phase to the recycled stream. So if you don't have this purging stream, the nitrogen will be recycled all the time. There's no way out. Okay? So input is C2H4, O2, and N2. And the output stream for the products will be ethylene oxide, 100%. This is very good, right? We like 100%. Okay, so, and here is gas phase. You just need to use a condenser because reactor might be in a high temperature. So this might be in gas phase, it condense, right? So gas phase becomes liquid phase, and then the purging stream will be some of the C2H4O and C2H4O and N2, O2 and N2. Okay. Okay. Right. So let's go to the example 4.7-3. They are in page 133. And I think this question will be, I think might be 100%, 75 to 100% in your midterm exam paper. Okay, so I want you to work with me on this example, and then you will get good scores in the end, okay? But before we really go to this example, let's refresh ourselves first. Let's play Kahoot. Right, let's go to the text.你可能要自己画 flow chart， 这题你可能要自己画 flow chart， 好不好？ Okay, let's go to this. The example 4.7-3, recycle and purge in the synthesis of methanol. Okay, so you want to synthesize methanol, right? Oh, sorry. Synthesize methanol. Where is that? Oh, wait. Okay. Right, so this is the chemical reaction. Carbon dioxide plus hydrogen become methanol plus water. It's easy. But you want to build it in a factory, in the industrial scale. Okay, the methanol is used as a raw materials in the manufacturing of the formaldehyde, acetic acid, methanol tetrabutane acid, and the numbers of the other important chemicals. Right, it is also has many other uses, including blah 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 blah. Okay, right. The second paragraph, the fresh feed to the methanol synthesis process contain hydrogen, carbon dioxide, and 0.4% moles inert. Okay, so you know there are three types of species as a feed in a reactor. Okay, they are hydrogen, carbon dioxide, and inert gas. Why we need inert gas in this system? Because if you put the pure hydrogen, 100% pure hydrogen into a reactor, it might be cause danger because hydrogen is a flammable, explosive gas, right? So you need to have a purging gas. You need to have a kind of inert gas, so the concentration of the hydrogen won't be so high. Okay, so the second line, the reactor influent passes to a condenser that remove essentially all of the methanol and water form, and none of the reactants are inert. So you have a reactor and you have a recycle stream. You have a separator, right? So that's what we know. So later, substances are recycled to the reactor. So it was recycled. To avoid the buildup of the inert in the system, a purging stream is withdrawn from the recycle. So this is this is the concept we learn, right? So what I want to tell you is that we have fresh feed to a reactor. So there are three species. One is carbon dioxide, hydrogen, and inert gas, which is about 0.4%. And then you have a reactor. And then for some reason, you will have a condenser, which is separator. So you condense and you separate liquid and liquid and gas, the product in the liquid phase and product in the gas phase. And of course, you got products, which is methanol in liquid phase, right? So all the things in the gas phase you recycle back to the reactor and join together with the fresh feed. Okay, so this is, and then because you have an inner gas, and inner gas will build up in this system, so you need to have a purging stream. This is recycle stream, and you need to have a purging stream. You need to have a purging stream. Okay, you need to have a purging stream. So this is all we know according to this information. Okay, so please work with me, and let's go to the third paragraph. The first line, the feed to the reactor, blanket, not the fresh feed to the process. So the feed to the reactor, okay, contain 28% carbon dioxide, 70% hydrogen, and 2% inerts. So let's write down the information we know in the flow chart. So we know that the total fresh, this has a 28% carbon dioxide, right? And then 70% hydrogen, and 2% inner gas. Okay, this is what we know, so let's write down. And then the third paragraph, line 2, the single pass conversion of hydrogen is 60%. So this is first specification for the single pass conversion. You know the single pass conversion is in the slides here. Single pass conversion is reactor, right? Okay, and then calculate blah blah blah. Okay, calculate the molar flow rate and molar composition of the fresh feed and the total moles of the reactor, the recycle stream and the purge stream for the methanol production of the 150 kilomoles methanol per hour. So you got only one number, which is 155. What is this? So if you take a look at the slide here, that will be the products. The product tells us that single pass conversion here, right? The product is, in the end, I want to get 155 kilomole per hour output for the methanol. Okay? So this is all the information we know. And you know, of course, this example asks you many questions, many unknowns that you need to find out. But don't worry about that first. Let's start to do DOF first. So once you know, this is all the information you know, and you can start from here. But the trick is that if you start to work on this, according to this information, you are going to have trouble. Because it's not easy. So first of all, this example asks you to forget about this one, 155. Forget about this one, and you have your number here, 100 here. Why? I tell you why later. I tell you why. Because you have all the ratios here. So if you complete this stream, it might be easier for you to find out another streams. And once, for example, if you got the answer of this methanol, which is about 15.5 more kilomoles, that means you need to scale up 10 times for each streams, right? Okay, so forget about this first, and when you get the answer, you know how many times more or how many times less from the original amount to the amount you calculated. Okay? So that's all the information we know, and now let's put the unknowns in this process and let's find out whether we can get answer. So we already write down one specification here. So let's have an input which is N0. I suggest you to have the same symbols to let teaching assistant easy to score, right? Don't give them trouble. Otherwise, you give yourself trouble. Okay? So use the same symbol to represent what you want to know, what you want to get the answer. So N0 is here, and you have 4%, right? 0.4%, right? So you can put X here, which is O. X0 is here. C stands for carbon dioxide. So for hydrogen, you have Y minus 0.004 minus X 0C, right? Because these three together will be 1, because this is fraction. This is overall. This is total amount. Okay? And after this, you have to complete all the information you know in this case. And single pass conversion here, so you put the unknown here. Because there is no fraction, so it's easier for you to put the total moles here, which is N1, N2, N3, N4. N1 stands for carbon dioxide, N2 stands for hydrogen, N3 stands for methanol, N4 stands for water. And in this case, of course, you can have N5 for inner gas, but you understand, inner gas is not, there's no chemical reactions for inner gas. So 100 times 2 equal to 2. This is 2 already. So you don't need to worry about this. Okay? Okay, next is that because this is a condenser, so this separate, there are 5 species. So you separate 3 species in the gas phase and then 2 species in the liquid phase. So as a result, C2H3O, this methanol should be N3, right? This one should be equal to this one. Why? Because this is a condenser. This is only the way out for the methanol, for the ethanol. Sorry, this is methanol. Sorry, methanol. So water N4, here is N4. So you don't need to do this N5 and N6 in this case. Right, and then you might say, well, Professor, can I do, so this will be N1, right? This will be N2, this will be 2. Can I write down like this? Yes, you can. But you will have trouble once you do this separate, when you do the input to output for these 2 streams. So the books suggest you, the textbook suggests you have total amount, which is N5. And then you have carbon dioxide, which is X5C, this stream 5, right? So this is 5C, X5C, X5H. X stands for fraction. Remember? Fraction. Okay? And the reason you want to do this is because this is splitting point. The fraction will be the same. So you will reduce the unknowns for this process. Right? Because if the fraction of this stream, N5 stream, is X5C, X5C, so this one will be S5C, S5C. Right? So split point has the same molar fraction. So you can write down the same one. So what you need is P stands for purge. Okay, so this fraction will be equal to the same as this fraction. And this fraction, R stands for recycle, will be this fraction, 3 fraction will be the same. So you reduce the unknowns in this case. So there are 2 keys in this question. The first one is forget about 155 first. Put 100 in this case. Key 1. Key 2 is using the same amount or more for methanol and hydrogen, water. And again, the key 2 is using the fraction for this purging stream and recycle stream. Okay? Well, you must think of 3 keys. Key 1, key 2, key 3. Key 1, key 2, and key 3. So when you do your midterm exam, please remember this. It will make you easier to get an answer, to get the right answer. Okay, don't put yourself in trouble. Right. Am I a nice guy? Okay, I tell you everything, but if you don't listen, I cannot do anything for you. Right, so the solution is that, please read this. In the general rule, a combined feed of the reactor is a conventional stream to use as a basis to calculation for the recycle problems. So you might say, well, Professor, why can I use 100 here, not here? Yes, this is the answer I want to tell you. It's more convenient for you to based on the calculation for the recycle. Okay, when the stream composition is announced, we will therefore temporarily ignore specific mole production rate, which is 155, right? 155. Balance the flow chart for assume the basis and the scale, and then scale the process to the required extent. So this is 155, right? But we put this as unknown. Remember, this is 155, but we assume we don't know this. So once we got this as a 15.5, that means you scale up 10 times. So all this need to scale up what? 10 times. Okay, all the moles need to scale up 10 times. Okay, so step 2, basis 100 moles combined feed flow chart. You draw the flow chart and you do the DOF. So this is the flow chart we did. And we mark all the unknown, we give all the numbers and mark all the unknowns in this process. Okay, again, let's do DOF in logical way. DOF first, overall system, right? Overall system. So you need to tell me, because overall system involves chemical reaction, so you want to do atomic species balance. So there are 4 terms for you to do DOF. What's the first term? First term is unknown, right? Second term is how many independent atomic species. The third one is molecular species balance. The fourth one is specification. Okay, so let's write down how many unknowns in this overall. How many? There are one input, right, and 2 output. This is 1 input. This is 1 here. 2 output. 1, 2, 3, 4, 5, 6. Right? Where are 7? I'm sorry. 1, 2, 3, 4, 5, 6, 7. I'm sorry. Sorry, I missed 1. So there are 7. So how many independent atomic species balance? How many? You just get the right answer in Kahoot, right? 1, 2, 3. Carbon, hydrogen, oxygen. How many molecular species balance? 1, right? Which is inner gas. Do we have a specification involved input and output here? No. The only specification we have is this one. So that's 0. So 7 minus 3 minus 1. I'm sorry, you cannot get answer of this 7 number. You cannot get the answer of these 7 unknown variables. Okay, so let's go to single system first. Single unit system. Go to reactor, because we understand you have specifications. So you don't want to do it here first. You don't want to do it here first, because we understand this might be we might get the answer quicker using the unit which has a specification. So single reactor. So atomic species balance. Again, another 4 terms, right? So how many unknowns in this case? 4, right? N1, N2, N3, N4. 4. How many independent atomic species balance. How many? In what chemical reaction, that will be 3, right? Carbon, hydrogen, oxygen. How many molecular species balance? That will be 1, right? But why I use blanket here? Because you already use inner gas. There's no unknown here in this case, so you can forget about this one. Because 0.02I will be 0.02I here. There's no unknown in this case. Okay? And how many other equations relating unknown variables? 1, right? Overall conversion. Oh, sorry, single pass conversion here. Single pass conversion, which is 60% of the hydrogen. So 4 minus 3 minus 1 now be equal to 0. Bingo. So you can achieve N1, N2, N3, N4. So let's enlarge this flow chart. Let's enlarge this flow chart here. So according to input equal to mass balance for the reactor, you get the answer of N1, N2, N3, N4, and let's change the color from red to blue. That means you solve the problem. And because you understand N1, N4, N3, N4 is the same in this stream and this stream, so you immediately get these 2 answers. Okay? Right, let's find out whether we can get other balances or not. So you do the condenser. Because you know there's only one string unknown, and here is all you got the answer of. Already get the answer, so you do the condenser. So condenser tell you what? N5. So you can achieve N5, NXC5, and X5C and X5H. Why? Because there's input equal to output, 3 species, right? Carbon dioxide input equal to carbon dioxide output. Hydrogen input equal to hydrogen output. Inner gas input equal to inner gas output. So you have 3 equations, and you can get the 3 answers. Okay? So you got this 3. And immediately, because you know this is splitting point, and the fraction here, because of 3 splitting point, so the fraction in the split purging gas, purging stream, and the fraction of for the recycled stream will be the same. So X5C here, X5H, X5C, X5H is the same as this one. So you get answer immediately. So there are only 2 unknowns here, only. Okay? So I change the color to let you understand. So again, you get the answer of these 4 first, and immediately get the answer of these 2, and then use the input molecular species balance. You got the answer of these 3, and because this is a splitting point, so you get the answer of these 2 and these 2. And now, only 1, 2, 3, 4. There are 4 unknowns in this case. So let's go to a splitting point. Can we do a splitting point? No. You have 2 unknowns. And you might say, well, but there's 2 unknowns, so input equal to output. And carbon dioxide input equal to carbon dioxide output. And hydrogen input equal to hydrogen output. So we can get an answer. No, I'm sorry, because these 2 equation, or there's only one independent, so you cannot get MP and MR using the splitting point. So not independent. So ratio of space is the same. This ratio is the same. So there's no this is not independent. There are 2 equations, only one equation independent. Okay, that's why we don't want to do splitting point. Let's do the mixing point. missing point. So the missing point, you have 3 unknowns, right? N0, X0C, and NR. So you have 3 unknowns. And this one doesn't involve any chemical reaction, so you just do molecular species balance. So, carbon dioxide, hydrogen, inert gas. Bingo. You got an answer of these 3. Okay? And once you got the answer of these 3, and you have N phi equal to NR plus NP. So, of course, you get the answer of this one. NP. Okay? Sorry. Okay? Achieve the NP. Right. So that's what you already did for this. So please do the calculation by yourself. I don't want to waste your time. You have example here, so you got these all answers. Okay, next one is flow chart scaling. This is another key, because remember we already know this is 150 pi per hour's output for the methanol, but we make it as an unknown. So once we got N3 over that means we need to do the scaling, right? We need to do the scaling. So 100 kilomole combined feed is N3, we got 14.0 kilomoles. So this is N3 is 14.0 kilomoles. Instead of 155, that would be 14. So you need to do a scaling, right? So real N3 is 155. So that will be 11.1 times more. So all the N0, N1, N2, N3, N4, N5, you need to, NP and NR, you need to times what? This is the number, you need to times 11.1. And that's the right answer. So that's what we call scaling. So if you go to the table, 142, you can get a scaling table. Okay? Right. So let me remind you again. This example is very, very, very likely to be in your midterm exam. Please go home and practice 3 times. That's wonderful. You can get good scores. So the key points for the example 4.7-3 is that choose a basis in the feed to the reactor, right? And then scaling. Splitting point, the same molar fraction, important, okay? And the independent species, every stream has the same molar fraction. Okay? Well, you can think in another way, key 1 or key 2, key 3, right? Key point. Right. This is the things that happen. Really recycle stream and purging stream in the industry. So this is methanol. You know, methanol is produced in the United States, and you don't want to deliver methanol to Taiwan. That's too far, right? Or Middle East, it's too far. So methanol is expensive to ship. You don't want, because methanol is very lightweight, and you know this cylinder is very heavy, so it's very expensive. You just carry very heavy things, but the things you want to ship is very light. So it's usually converted to a carbon monoxide and hydrogen. So normally you convert to what? Benzene. Like methane convert to benzene and water. So you don't want water, right? So you just ship benzene. Benzene is liquid. So you just ship liquid. You can ship a lot of amount, right? And then, so this is a reaction you need to involve, which we call methane dehydrogen atomization. Okay, you use MDA for sure, and this is the process. So as a result, you can ship the liquid instead of gas, and save more economic, save money, right? Right. So that's it for today. I think for the for the section 4.7. Okay. I think I better stop here because we still have 3 minutes, right? 3 minutes. So I just want to let you know that your methane exam doesn't involve section 4.8, okay? 4.8不会在期中考考你，好不好？那我只是简单的介绍一下。So this chemical reaction, this is combustion. The things for combustion is very interesting is that normally if you have a chemical reaction, what you need is product, right? Because you need product, and then you have some unreactive reactant and you recycle. But for the combustion reaction, you don't like products because product is carbon dioxide. So what you need from the combustion reaction? Energy. You need energy. You don't want products. Okay, you need energy. So this energy is that, for example, you have coal, you have oil, gas. That's what Taiwan uses, right? And what you need this is chemical energy. Right? Chemical energy convert to what? Chemical energy convert to thermal energy. Thermal energy convert to mechanical energy. And mechanical energy convert to electrical energy. So you got electricity. That's the power station. So it's the matter of you use coal or oil or a gas. They are all a form of energy, chemical energy. Of course, if you talk about nuclear reaction, that's another story. Otherwise, for the coal, oil, or gas, they all produce energy. They are energies. Okay? So then what is chemical engineering and related to combustion reaction? This power station normally involve two types of engineers. One is chemical engineers. One is mechanical engineers. A chemical engineer is related to the reactions. The mechanical engineer is related to this process. Okay? This is the biggest power station in the United States. Right. So, combustion chemistry involves fuel. Fuel is energy, right? You can have solid coal, liquid oil, and liquefied petroleum gas, or the gaseous fuel, natural gas. Right? Natural gas involves 85% to 90% methane. Okay? That's what we are going to buy from the United States, right? Okay. Because of Trump. Right, okay, so this chemistry. So when you involve oxygen, normally again, I want to tell you is, you don't burn oxygen. You don't burn pure 100% oxygen. You want to burn what? You want to burn air. Right, because air is cheaper than the pure oxygen. Okay? So expensive reactant normally is a limited reactant. And cheap reactant, which is excess reactant, in this case, for chemical reaction, for a combustion reaction, is air. Okay? Right, and I think I will stop here today then. I think that's it.